You know, when you look at some of the most complex systems in the world, from the stock market to the laws of physics, don't you ever get the feeling there's gotta be a simpler structure hidden underneath all that chaos? Well, it turns out there usually is. And today, we're going to talk about the mathematical key to finding that hidden order.
Okay, let's jump right in with a little mystery. Take a look at this equation. Now, at first glance, it doesn't look that bad, right? Just some x's and y's. But what if I asked you to actually sketch it, to draw the shape it represents? Yeah, that's where things get tricky. It's not a simple circle. It's not a standard ellipse. So what on earth is it?
So the source of all our problems, the real troublemaker, is that little negative 2xy term right in the middle. As the quote here says, nobody panics about the squared terms. But you throw in that one little cross term, and suddenly everything gets complicated. It's the villain of our story because it takes what should be a simple shape and twists it, rotates it, and completely hides its true identity from us.
All right, so to deal with this villain and crack this mystery, we need to find a totally new way of looking at it. We need a special tool from linear algebra, one that's all about finding the directions that don't get twisted, the ones that stay stable while everything else is changing around them.
And that brings us to the hero of our story, the eigenvector. So I want you to imagine a big transformation that's stretching, squishing, maybe even rotating an entire space, right? Well, an eigenvector is this one special vector that just refuses to change direction. It stands firm. It might get stretched or shrunk, but it will always point along the exact same line it started on.
And every hero needs a sidekick, right? Well, every eigenvector has its partner, the eigenvalue. We usually write it as the Greek letter lambda. And all it is really is a number, a simple number that tells you exactly how much that eigenvector got skilled. Did it double in length? Did it shrink to half its size? Maybe it even flipped around and pointed the other way. That's what the eigenvalue tells you.
And this diagram here just perfectly illustrates the whole idea. See how most vectors would get spun around all over the place? But look at x1 and x2. They're the special ones. When the transformation hits, they stay right on their original lines. Vector x1 gets scaled by an eigenvalue of 1, which means it doesn't change length at all, and x2 gets scaled by 0.5, so it shrinks by half. These are the stable, unchanging directions of this whole system. So this all boils down to one beautiful, simple equation, AV equals lambda v. And this is the whole magic trick right here. On the left side, you've got this potentially complicated matrix multiplication, but on the right, it's just a simple number multiplying a vector. For an eigenvector, those two totally different operations give you the exact same result. This is the key that unlocks and simplifies everything.
So this is all great in theory, but how do we actually find these special vectors and their eigenvalues for any given matrix? Well, it turns out there's a pretty clever step-by-step procedure to uncover them.
Now, this might look a little intimidating, but the core idea is actually pretty straightforward. We start with our main equation, AV equals lambda v, and just shuffle it around a bit. And here's the key insight. For this whole thing to work for a non-zero vector, a special property of that new matrix, its determinant, has to be 0. And that condition gives us a new equation, the characteristic equation. All we got to do is solve that equation for lambda, and boom, it just spits out the secret eigenvalues of our system. All right, now that we've got our super powerful new tool, we can finally go back to that mystery equation from the beginning. Let's see how finding these eigen things cracks the code and reveals its true shape.
Okay, step 1 is to rewrite our equation using a matrix. And look at what happens. That pesky xy term, it becomes the numbers that are off the main diagonal in this matrix. Those little minus ones, that's the mathematical source of the rotation that was giving us such a headache.
And here's where the magic happens. It turns out the eigenvectors of this matrix point along the natural axes of our hidden shape. Think of them as the special directions where all that rotational complexity, that annoying cross term, just disappears. It's like we finally found the perfect angle to look at this thing. And here it is. This is the payoff. On the left, you've got our original complicated equation. But when we switch our perspective, when we change our coordinate system so it lines up with the eigenvectors, those natural axes we just found, the equation totally transforms. That messy cross term just vanishes. And what are we left with? The simple, elegant equation on the right. Now that is an ellipse we can all recognize and easily draw. And just like that, the mystery is solved. Our weird, confusing curve was just a simple ellipse the whole time, but it was rotated by 45 degrees. The eigenvectors didn't just give us the answer, they gave us the right perspective to see the problem for what it truly was.
But hey, this isn't just some clever trick for drawing shapes. The power of finding a system's natural, stable directions applies pretty much everywhere. It lets us understand the long-term behavior of all kinds of dynamic systems, from biology and finance to technology.
So to see how this works in a dynamic system, check out this matrix. It comes from a biology model that describes how a rabbit population, which is split into 3 age groups, changes over time. Basically, you multiply this matrix by the population vector for 1 year, and it tells you what the population is going to look like the next year. Now, if we do our procedure and find the eigenvalues for this rabbit matrix, we find that the biggest one, the dominant eigenvalue, is just a single number, 2. And believe it or not, this one number holds the key to the rabbit population's entire future.
So what does that dominant eigenvalue of 2 really mean? It means that no matter what the population looks like at the start, whether you have a lot of old rabbits or young ones, after enough time passes, the system is going to settle into a stable growth pattern. The population will eventually just double every single year. The eigenvalue reveals the system's true long-term behavior.
And the applications are just everywhere. I mean, they're used to figure out the exact frequencies that could make a bridge vibrate dangerously. They're in the control systems that keep airplanes stable. They're at the very heart of quantum mechanics. Even Google's original PageRank algorithm was basically just a massive exercise in finding the most important eigenvector of the entire internet.
So what's the big takeaway here? What's the fundamental truth that eigenvectors and eigenvalues are really showing us about how the world works? Well, the name itself gives us a huge clue. Eigen is a German word, and it means own or characteristic or typical. And that's exactly what they are. Eigenvectors and eigenvalues aren't just random math results. They reveal the deep, intrinsic, characteristic properties of a system.
You can think of them as the system's hidden skeleton. They show us its principal axes, the directions it prefers to stretch or shrink along. They show us the stable states it wants to settle into. And they show us the fundamental frequencies at which it naturally wants to vibrate. They reveal the true, unchanging nature of a system, hidden beneath all the complexity. And that leaves us with one final, kind of out there thought. We've seen that these mathematical systems have natural directions of stability and change. So what if you could find the eigenvectors of your own life? You know, those directions where putting in effort leads to simple, stable growth, instead of complicated twists and turns. What would they be?